So in the last lecture, what we saw was basic definitions and I think how to find the velocity of center mass and how to find the acceleration of center mass. Yes. So I think we have done the ACM part, right? The acceleration of center mass.
Yes, sir.
And we realized two things. That to find the acceleration of center mass, either you calculate the net external force acting on the system which you are considering and divide by the total mass of the system. And this also turns out to be I can just write in short. So there are two ways. Like this, or you can say these are two perspectives. So if you know the forces and if you want to find the ACM, just divide the net force by mass, or you can just write the Newton's second law. But in many situations, you will find that it is easier to find the individual acceleration than the uh, net acceleration of system. So if it is easier to find the individual acceleration, then the second method will be better for you. Okay, so that is the idea. So today we are going to see some of the numericals which are based on calculation of AC. So let's do the so we have a pulley and let's attach two masses. So we can call it and let's say M2 is heavier, so it's going down, and definitely if M2 will go down, then because of the constraint, M1 has to go up. So if I ask you, will they move with same acceleration? Yes or no?
Yes.
Yes.
So my question is, will they move with same acceleration? Yes or no? Tell me, guys, yes or no?
Yes.
No.
No. Okay, so that's the problem. They are not moving with same acceleration. They are moving with the same magnitude of acceleration. So it may look very trivial, but it matters a lot in physics. Acceleration is a vector quantity, and so if directions are opposite, it means they are not the same vector. They are opposite vectors. So what we can say that M1, M2 will move with the same magnitude of acceleration, not the same axis. So indeed they are moving in different directions. And now if M2 is going down, which means out of M1 and M2, inherently I have assumed that M2 is heavier and M1 is lighter for the sake of analysis. So when I'm doing some analysis, so I thought of let's call M2 as heavy. Now M2 being more than M1, it will make some sense to you. So which mass moment is going down. So as M2 will fall down, I can say the mass moment will shift downward for M2. And what about M1? So M1 will shift the mass moment upward. So if you choose some random origin in some arbitrary location, then there is some mass moment M into R vector. So R is the position. And what I'm saying is that as M2 will descend, the mass moment vector will shift down. That is what I'm saying. Okay. So mass moment vector will shift down, and M1 will shift the mass moment upward. Do you realize this? Yes or no? Not all probably.
Can you repeat, sir?
I'm saying M2 will go down. So the mass
Yes.
moment M2 will go down,
Yes.
because what do you mean by mass moment? Mass into position vector.
Position.
So okay, maybe you are not realizing. Let's say this is the M2 location. This is some origin. As M2 will descend, this is a new position vector. If it is the R2 vector, and if it is the R2 dash, so what was the initial mass moment? M2 R2. And what is the final mass moment? M2 R2 dash. So what is the difference of the same? The difference means M2 R2 dash minus M2
M to
R2.
R2 dash from the center.
And if you look carefully, this will be something like this. So this is called the shift in mass moment. So as M2 will descend, the mass moment will shift downward. This is what I'm saying. But at the same time, because M1 is also there, so maybe M1 was here. Okay, let's see. And now M1 goes up. So what you don't realize that the mass moment of M1 has shifted upward, and the shift will be, if I call this as Y, so one will shift upward, and let's say this is also Y. Luckily, Y will be same, because as much as it descends, the same it will ascend because of the obvious constant relation. So if you look at the mass of M1, M2, which one is bigger? M2 is bigger, that's why it's going down. So there is a
Yes.
downward shift of the mass moment, which you don't realize in general. There is a downward shift of mass moment, and there is an upward shift of mass moment. The upward shift is carried out by M1, but the downward shift is carried out by M2. The upward shift is Y, and so the downward shift numerically. If this is the increment in mass moment, then I can say this is the decrement in mass moment. Now you tell me which mass moment shift is dominating here, this or this? That's the first question. So which shift is dominating? So is it M1Y is bigger in value or M2Y is bigger in value?
So both are
M2.
same.
So definitely it's M2Y, because M2 is heavier than M1. So because M2 is bigger than M1, so shift downward is dominated and shift upward is lesser than that. So if you look at the system as a whole, the center mass must be shifting in which direction, down or up? The center mass will shift in which direction, up or down?
So can you repeat question?
The center of mass will shift up or down. That's simple question.
Down.
Correct. Because the dominated mass is M2, so it will bring the center mass eventually down. And that's common sense. So let's say if there are two masses, One is 10 kg, other is 5 kg. Now, if 5 kg will move by this much and if 10 kg will move by this much, so where do you expect the center mass will be? Above this line, below this line?
Below the line.
So definitely the center mass is going down, and it should be. In fact, because the heavier mass will actually decide the eventual movement of center mass. So when you release a simple two block system from rest, you may see M2 going down, M1 going up, but what you don't see in general, because that's not how we are taught to see, that the center mass always descends. So that is something that we need to develop as a visualization. We need to come up with this perspective more often than ever, that in the entire process the center mass is descending now, and because each mass is accelerating, and you know the acceleration because you have done the Newton's laws of motion chapter some where in the past. So I presume that you know how to calculate a individually. Okay. And now because I know that center mass is descending down, and because each part of the system is having some acceleration, so I can say from here that the center mass must have some acceleration. So now my obvious question is, what is the acceleration of center mass? Like what is the rate at which that center mass is descending, which you don't realize in general. So I want to know the rate of acceleration, the acceleration with which the center mass will descend. That's what I'm looking for, and that is what I'm trying to calculate. So one way which we know, if I go with the first definition, let's try to derive this from the first definition, which you don't see very often. And in fact, I will not say that you need to be doing in that way, because that may be cumbersome at times. So now, before you do anything, draw the ABD. Now, there is some question which I will ask you, and you have to answer it with logic. Okay. So my first question to all of you is that the tension force is internal for the system of M1 M2 or external. So what do you think about T? Is it internal to system or external to system? And my system is M1 M2,
Extra.
external. Anybody else having different opinion than this? Like you want to say something which is not this answer? So M1, sorry, M1 and M2 and M1G, M2G and T. So all these forces are external. So T is indeed external force here. So what is the ACM by definition? So let's write the ACM magnitude. So I'm removing the arrow sign because I just want to write the value. So what is the magnitude? I mean, what is the value of ACM? Using the first definition. Tell me. I hope you know how to write the net force. So what is the net force?
So it's empathy minus M1G. One.
It is M1 plus M2 into G, because that is dominating M downward minus 2T. And what is the total mass of system?
M1%.
Now, if I assume the acceleration as A, and if I choose the upward as positive direction because it's one dimension basically. So what is the second definition? Because this must be also equals to the second definition, which says that what it says. Come on, guys, tell me. what it says,
Mass.
what I can write here. Tell me. Okay, now ACM is downward, so I want to write the downward value. So I can say, okay, I have to take the downward as uh, positive and upward as negative. No, in that way, because I'm taking downward as positive. So let's take downward as positive and upward as negative because I'm trying to write the value. So as per the second definition, what I can write? Tell me.
So
Hmm?
summation of all mass transmission.
So what should I write? Like, can you dictate what should I write? Anybody?
M2A minus M1. Sorry,
In
M2A plus
not
on
which
integration minus M1 upon
upon.
M1 to C.
Yeah, these are vectors, so you need to be careful with sign. Now these are two possible ways of solving the question, and of course this is downward. I'm taking the direction downward as first. So if you know the Newton's laws of motion, can you tell me what is the tension force for two block system? Because this is very famous.
2 nu G.
Correct. It is two reduced mass into G. And the reduced mass will be like 2 m1 m2, the product of
100%.
summation into G. Very good. So now because you know the tension and in fact you also know the acceleration, the A is small a value, and that is the difference of mass upon summation. So if you substitute the T here, the answer you will get from the first method. And if you substitute A here, you will get the answer from the second method. And for the sake of verification, you just need to do this calculation right now, right away also. And tell me that both answers same. Like of course you have to verify by doing. So we know inherently that this must be same, but now you have an opportunity to do on your own and realize this. So I'm giving you 2 minutes to do this calculation. Tell me the answer, the final answer, using both methods. Everyone, right now. I hope I'm audible to all.
Yes.
Okay. So do this question and tell me the answer. I hope it's done. So anyone getting the answer? Your only job was to substitute. I mean, I don't know if I'm not able to do this calculation, then yeah, competition is going to be very difficult for you guys.
Done, sir.
Yeah. So what is the ACM you're getting? The value, numerical value.
So it's M1 minus M2 upon M1 plus M2 whole square into G.
Yeah. So it's M2 minus M1, M2 plus M1, and it's downward. Or if you want to write in if you want to write ACM y value, y component, then I should write minus of the same because y I'm taking upward. So okay, depending on the now I don't want to put that because I have taken the sign. So if you do by the both method, you will get the same answer. Now in most of the situation, the second you will find the more convenient. Uh, so you may use the second, but the first method is very important from the perspective of sorry, rotational dynamics. So the very next chapter demand Newton's laws of motion to be written for the rigid bodies, and in case of rigid body, the first becomes the prominent stuff. So that is something we have to be good with for the sake of next chapter. Okay, so how many of you are able to derive this? I mean, if anyone who is not finding it very difficult, let me know. I'll just do it for you. Anyone finding it very difficult? Just let me know. Don't hesitate. You can say,
How did that introduction?
pardon.
How can introduction?
Anyone finding it difficult? I'm saying if you're finding it difficult, then answer. If you're okay, then I can go next.
So, okay, sir.
All right. So let's do this problem. It's a simplified problem, and of course you can do by the first method. There is no doubt about it. But even I will suggest that okay, you just go through the second method because that is more convenient. Okay, guys. So tell me what is the ACM, and now you have to write in ICAP JK. First of all, can you tell me that center mass is moving in which direction? Is it moving along X or Y or somewhere in between? You take a right as positive, up as positive, and I want my answer in terms of maybe ICAP and JK. So what is the ACM now for this system in vector notation? So if you want to give it a try, you can give it, and then probably I'll solve. So I'm giving you 2 minutes. You can try if you want, but anyway, I'll give you the solution. So if you really try, it's really good for you. That's it. Anyone who is trying, or shall I give you the solution then?
So trying.
Okay. So do you realize in which quadrant the center mass is moving? First, second, third, fourth, which quadrant?
Fourth quadrant.
Correct. Very good. And about in which the axis is moving like faster, like the angle it is making. If you look at the direction mentally, can you tell me the angle made by x-axis is more than 45 or less than 45?
More than 45.
Correct. Very good. Who said this?
Oh,
Atharv.
yes.
Very good. That's the correct answer.
So minus 2g by 9.
Minus
Minus 2g by 9.
2g by m.
9, 9.
9, 9. But that's it.
Yes.
It's definitely wrong. Okay, so look at this. Now we know from laws of motion that if this will go down, I mean this will go right, that's the only way. But they will go with same magnitude. So the magnitude of acceleration is going to be same, but of course a different direction. So center mass will move right and down, but downward is heavier mass. So this movement is faster. The mass movement will descend faster, and the mass movement will go right slower. So the center mass will eventually move something like this. So this is the ACM direction that I can conclude from the mass ratio and all that. Sorry. So what is the A value? So A value we know is the net pull force. So the net pull force on a system is how much? So we all know from laws of motion is
2
2
mg
mg, and the total
upon
mass.
3m.
That's correct. So this is 2g by 3. This is the numerical value.
Yes.
But what I said is what is the ACM? What is acceleration of center mass? So I have to write M in.
2g I cap minus 4g j cap by 9.
So what I'll write is M into A into I cap plus minus J cap. So these are in different directions. So The only way we can write is vector form. We cannot write it numerically because it's not one dimension motion. And if we divide by the total mass, which is 3. Now this is how we have to write. ACM turns out to be A by 3 I cap and 2 by 2A by 3 minus J. All right, so we got this ACM. And A by 3 is how much? It's a 2G by 9. And this will be 4G by 9. So this is a way of writing the answer of ACM. Or if you want to find the magnitude, if you want to take the modulus, you can take it just like the way you do. So it's 2G by 9 a common, and then it's 1 square plus 2 square, which is root 5. So the answer is 2 root 5 upon 9 into G. That's the magnitude if you want to find. So of course, I mean, it is a very common practice that many times you do not realize that when you solve the uh, ACM formula, when you apply the ACM formula, it's a vector equation. It's not a number. And generally, from your past experience in laws of motion chapter, you don't realize this particular fact that I need to write in vector form, because there we write the magnitude only, and we do not write the direction. So this kind of mistakes are very common, and you can definitely avoid it in future if you just put a small thought to the what we are doing. And if you look at the component, it's definitely twice. The J component is twice of the X component. So that's why if you look at the diagram which I had drawn, the vertical I have drawn is double length than the horizontal. And that's the reason I was knowing that this is going to be twice. And for the opposite, why it is twice? Because we know that this is 2m and this is m, and a being the same value, so numerical value of a is same, mass is double, so the downward shift of the center mass is at twice rate than the horizontal shift. So these are the things which you can visualize easily without doing any calculation. So of course calculation may be asked, and sometimes they will ask you only a graphical graphical picture of what's going on. Okay, so all right, so these questions are important. So if you're okay with the vector notation, and if I just want to level up the answer, okay, so this is the question. So we have a wedge. A wedge is some triangular shape object. In physics we call wedge. And of course I'm doing the same problem, pulley system. So now I have a two pulley which are placed on two separate inclined planes, and both the inclined planes are part of the same wedge. And wedge is fixed, so wedge is not moving, so no need to worry about the motion of the wedge as such. And maybe one mass is 2 kg and giving a minimal value. Let's take 3 kg, take GS10. Okay, I mean, may not be required. And then this angle I'm taking as be 53 degrees for simplicity, and this is 37. All right. And the x and y coordinate that you are supposed to choose is this. So I'm still taking the horizontal as horizontal towards the right as x-axis and vertically up as y-axis. Now your question is the same. What is the ACM in vector? So can you do this calculation? Anyone interested in this question? Doesn't seem like you guys are
Yes.
any
Yes, sir.
learning this chapter. See, this chapter is really one of the most challenging chapter for many students. Unless you will not participate in doing things, probably you will not learn this chapter at least. So I request participation of a different level, particularly for this chapter. So now you are actually learning physics, actual physics. So show your vector skills, like how to resolve vectors. So you know that you can just calculate the mg sin theta to check which way it will move. So this will be 3g sin 37, and this will be 2g. Just sorry, just check which factor is dominant. So 53 is how much? 3 4 by 5, which is 8 by 5 this side, and this will be 9 by 5. So definitely it will go this way. So now with this small analysis, you can realize that 3 kg will go down and 1 will go up. You can just check for yourself. Okay, so I given you the support minimum hint, and from here you can proceed and you can find the A and all. Okay. So those who don't know the Newton's laws of motion, which is not possible, everyone should know. You can write A equals to net full force along the plane upon net mass. So when you apply this formula, then the tension is not considered. We only check the end-to-end force. So you're supposed to write the A for individual block in vector notation. So that's the only effort which this question demands. The rest is pretty obvious and straightforward. So anyone who is not understanding conceptually what is going on, you can ask your doubts or raise hand.
So I can solve this one.
Yes.
So wait, so I'm solving. So
Okay.
sir, I got ACM vector in
Hmm?
vector form as 30 I cap
Hmm?
by 125 minus 2 j cap by 125.
Something like this, right?
Yes, sir.
All right. So let me write down for all of you guys. So I'm writing for 3 kg first, so you can check carefully what I'm writing. Okay. So first of all, the A is downward. So this is the A, and the angle will be definitely 37 degree. It is going to be 3A, the MA cos 37 I cap minus sine 37 J. This is mass into acceleration in vector plus for 2 kg 2A, and then you can see clearly it's cos 53 I cap plus sine 53 J, and then divided by the total mass, which is the obvious thing. Now here the challenge is just okay, not there is no challenge. Just to find the A, and A is simple. It's a net pull force, which is
2 by 5.
yeah, it's a 3 sine 37 minus 2 sine 53 all into G by 5. So this turns out to be how much? Uh, see, 9 by 5 and 8 by 5 is 1 by 5, and 10 by 5 is 2 by 5. So numerically, this is this much. I'm putting G as 10 to simplify this. So you can do it more rigorously if you want, but I'm just doing it. And now it is all a matter of a rearrangement of these terms. So 3 into cos 37 is 4 by 5 I cap minus 3 by 5 j cap plus 2 times of 3 by 5 I cap plus j cap, and entire term should be multiplied with A. So this is how much? This is 12 plus 6, 18 I by 5. Yeah, just check. And minus 9 plus 8, which is minus 1 by 5. And that is into A, which is 2 by 5 upon 5, which is, yeah, like this. Which is 36 I cap by 125 minus 2j by 120. So you, maybe some mistake you have done in calculation, but that's very close to the right answer. So this is the answer, and this is how we write it. So it may be slightly calculative, but these are the basic steps which you just need to follow, and you will be through the calculation. So anyone having any doubt in this so far? I mean, if you want to ask something, you can ask.
No, sir.
All right. Okay, so Okay. Now we have seen one particular problem type which you will face. Okay. So now coming back to the ACM. So what if ACM is 0, or the other way of saying the same is, what if there is no external force acting on a system? So what if the net external force acting on a system is either added to 0 or not acting at all? It's the same. So what if? So these are two questions which we need to answer. What if A and B? It's the same thing. So if you do not apply any force to a system, then the center mass will never accelerate. And if the center mass will never accelerate, which means there are two possibilities. So what are the possibilities?
So the velocity of center of mass is constant or 0.
Very. So the VCM we expect either to be constant if it is non-zero, or it is 0. It is not moving at all. So it may be stationary. So let's say if a system you observe in the very beginning that it was at rest, and if some commotion begins because of the internal interaction, you can say with full confidence that still the center mass is at rest. Now, for example, imagine you have a two small uh, maybe balls attached to a flexible string. You can say rubber band, something like this. And you stretch that spring or that rubber band across the end of which is some object attached, and you just put on the ground on a frictionless surface. So now inherently you know that the center mass is not moving right now, and then you release. So definitely, if you observe the subsequent motion, you can see clearly that both the objects are in motion. But we know that that motion has begun because of the attractive force or the spring force between them. So that's purely internal force. So what you can say that even in future, or because I release from rest, so the center of mass was at rest. So no matter how they move, the center mass cannot move. So center mass is still occupying that same location as it had before, and the particle's subsequent motion will not affect that location or the position of center mass. It means they will move in such a way that the center mass remains at the same place. And how we can reduce this fact? Because our journey began, like the particles started the motion because of the internal interaction, not the external force. And for center mass, external force is essential. That's a mandatory condition. If it is not there, there is no question of AC. So I hope this is clear to all of you. Now, if VCM is constant, then we can say something. So center mass will shift. So the location will shift. And shift of location is not the meaning that it is accelerating. So it is moving with constant velocity, so it will change its position gradually without accelerating. So the position, so this I can say this implies if this is the situation, you can say something. So this implies the center mass will have a shift, or we can say displacement. And this displacement we can easily write as VCM into time interval. So whatever time you choose, in time t you will travel by this value. So that's relation is very much valid whenever you see VCM is constant. And that's from the canonical equation. But even more interesting is this equation on the right. So this will guarantee that because the system was at rest in the very beginning, and because there is no external force, so the ACM, therefore the velocity will never change. So it was zero, it will remain zero forever. And zero means stationary. So center mass will not move at all. So the second condition will suggest that in a system in which the system was at rest in the very beginning and there is no external force acting, there is no question of center mass shifting its place also. So VCM 0 refers to, or there are many ways of thinking, that delta RCM must be zero. Now this is the very, very extremely important relation. Now, although I'm saying delta RCM 0, but this will not put a constraint on individual particles motion. So they may be shifting. So it is quite possible that the particles which consisted in that system, which is a part of that system, they may have some uninterrupted motion. So they are moving, and they're moving because of their mutual attraction or repulsion, whatever. But the due process of internal motion will never shift with the center mass. So that is a big takeaway from this discussion, that when VCM is zero and ACM is absent, then RCM becomes constant and delta RCM becomes zero, and this will lead to the a variety of form. So what are the formula which I'm expecting or you should expect? So RCM, if you remember that RCM formula, so that let me grab something. So we know that RCM we write as summation mi ri upon. But for this particular situation, although r may be the individual particles r may be shifting. So if I want to write the delta RCM formula, what I will write is this is equals to mi into individual shift, like shifting of each particle individually upon mi. But in our case, because this is zero, so this implies something very interesting. This implies that the numerator must be zero, which means individual shifts will be balancing, will be happening in a way to balance each other. So if one is going right, other is going left, they make sure that they will move in a pair to make sure that things are not moving, the center mass is not moving. So in a way, you can say that a natural process where there is no external interaction, or there is only internal interaction, even the the path we can predict. We know that the motion should have been only this particular way because that is how they can maintain their location of center mass. So there are a variety of things that we can visualize that this should happen because of these constraints. This is the only possibility that could take place in this particular motion. So those visualizations are very important. So now we are at a conjecture in this chapter, which is having the far-reaching consequence. So this tiny piece of formula will let you solve the most complex problem. I will say V important. This is very, very important formula, and it's a very, very small formula. It looks like nothing, but its application we'll see very soon. So now this consequence is very important. So this is the algorithm of thinking. I mean, if you're solving any question of center mass, you can think what is happening. Is it ACM 0 or non-zero? If it is 0, then what we can write? If it is non-zero, what we can write? And even if it is 0, then there are two possibilities. The system was at rest and will be at rest, or the system was in motion and will be in motion. And from there again further we deduce two particular formula. One, if the system is moving, then how much will shift its location over a time t. And if it is not moving, then what should be the relationship between the individual displacement? So in a way, the individual displacement is somewhere related. It's not actually independent. So it looks like independent, but it is somewhere, you know, having some pattern, like they connect with each other. So there is some pattern or some relationship between the individual displacement, which will occur in a way to make the sum zero. Mi delta ri, the sum must be zero. So we'll see the consequence of this particular formula. So that is what we are going to do next, like deriving a variety of formula based on this equation. All right. So anyone having any doubt in this? If you want to ask something, or shall I proceed next? Okay. So now having this formula called delta MIRI, I have some space left here. Maybe I can on this page. Okay. So now this summation MI delta is called the shift in mass moment. That is what I was talking about in the very beginning of acceleration problem, the shift in the mass moment. So if every mass will change its location, we say the mass moment will shift. And now let's say if you have 10 particles in a system, then each particle will shift the mass moment in its own right, independent of each other. But it turns out that they are not actually independent. They are somewhere dependent. And this dependency is being conserved by the nature. So nature knows what to do. And this is something beautiful about nature, that the nature creates these patterns automatically, and that is why we see the miracles of nature. So there is something going on in nature, and nature will have its own way of balancing things. And this is how we analyze through the knowledge of physics. So nature is having already all physics, and we might have extracted a fraction of that knowledge, a very small fraction. So far, all development of in science or physics or any other branch is derived from nature. So nature is having those things, but as a common human being, we are not able to see those pattern in a mathematical way. And then once in a century, of man is born with some unimaginable brain and thinking ability, and which changes the rules of the game. So that's always there. Now, when I say this is zero, I can also convert this into component. So this zero also implies that the delta xi is also zero. This also implies if the first term is zero, then this is the consequence. But the other way is not possible. So if this is zero, does not imply this is zero. This is not possible. If this is zero, this that does not imply this is zero. And why? Why this is so? So now you will see that in some case you may have external force acting in one particular direction. Let's call it x direction or y direction. So if the external force is acting along the x direction, and if y is seeing no force acting at all, then the conservation or the y shift, we can use this form. It means if there is no force acting in the y direction, then the center mass will not shift its y position. That's the idea. And if there is no force acting along the x direction, so y direction may have some force. Let's call gravity, which is very common. But x direction, there's no force. Let's say we have a frictionless surface. So we are deprived of force acting on the horizontal. Then the center mass can shift its y location, but it cannot shift the x location. So we can we can solve question based on this formula, and you will find most of the questions are based on the x one. This particular thing is more commonly used in questions. Okay, so That is what we are going to do. So let's begin the first problem. And I will try to also explain why this happens and like what exactly happens. But these are some alternative way of thinking. So this is not very much intuitive in the very beginning, but maybe soon you will also realize. So what I'm doing, what I have done here is called the plank. So let's say this is the plank. All right, so this is the plank. And this plank is kept on a frictionless surface. So there is no friction here. So the moment I say there is no friction and I say the surface is horizontal, indirectly I'm telling you that there is no horizontal force. Okay, sorry. So when I say there is a plank kept on a horizontal surface, I'm saying there is no friction at all. So I am totally eliminating the possibility of horizontal forces. All right. And now there is a man. So always the question is a man and the plank. This is called man plus plank problem. Man. So man and the plank makes my system. That is my system consideration. So this man of mass m and this plank of mass capital M is kept on a frictional surface. Now, of course, there is some friction between the man and the plank because that is essential to walk. If there is no friction, the man cannot walk. So that is something inherently hidden and it is not explicitly mentioned in the problem. But we can always realize that physics simply says that you cannot walk without friction. So man and plank is having some force, which we need to look. So the moment man will tend to walk on this plank, what he will do to walk forward? What is the basic steps that anyone or any person will do to move forward? What you do? So what you do is you press the ground beneath your foot backward. So the man will press the surface backward, isn't it? And then the Newton's third law will come into picture suddenly. That the man will press the plank backward, so the plank will apply the reaction force on the man forward. So what we don't realize in general that if you do the FBD of the man, there is a frictional force acting on the man. Let's call it static because that's what generally acts on when we walk. And at the same time, the plank will experience a force. Again, that is difficult to realize. Now, these two are action reaction pair. And these two forces are part of the same system. It's a internal force. So that is what I said. You must look for the system in which there is no external force. So internal force is always there. That's why they move relatively. So next, and from Newton's law, if you know that if there is a force, there will be some acceleration. So in a way, man will move forward and the plank will go backward. Now, this is the Newton's laws of motion way of discussing the thing. But right now, we are in a chapter called center of mass. So we have to change the perspective. So that is, of course, we always have a very fundamental tool called Newton's law of motion, which can give you some insight, like what is going on. But what if I want to look from the lens of center of mass? And this discussion is not appropriate for that perspective to come forth. So in order to understand the center of mass perspective, we will say this. So what we'll say? We say that The system in the very beginning, before the man began the motion, the system was at rest. The plank was at rest, and you were also at rest. So the moment you start walking, what you don't realize, the moment you start walking, you apply force on the plank in the backward action, and you experience force in the forward action. So you go forward, the plank goes backward, and the moment you reach the another end, by the time you are at the other end, the plank is not there. Plank has gone backwards somewhere. Okay, so this is one perspective. Now, St. Thomas says that because the system was at rest and the force between the man and the plank is definitely internal. So, if you look at the system called man and plank, do you see any like horizontal external force? Do you see any force? I'm taking man and the plank as a system. So, if you draw ABD, you will realize that there is no horizontal force acting on the system. So how many of you are able to visualize the same what I just said? None, or anyone who is not able to visualize what I'm saying? So that is the most crucial part of solving numericals. It's pretty simple, but it's pretty difficult to understand at the same time. And once you realize it, it's nothing. It's just a piece of cake. So do you realize what I'm saying? It looks like no one has understood.
Sir, can you repeat the question?
No, my question is simple. I mean, what I explained, do you understand what I explained just now?
Yes. Yes.
So you realize that the moment you started moving, the system was at rest. So the center mass. So center mass is somewhere which you don't see. Center mass is somewhere which you don't see, but wherever it is, I'm saying wherever it is, what do you think? Is it moving or is it at rest?
Rest.
Rest. Okay. Now the moment if the man will start walking on the plank, in order to now imagine this way: if the man is trying to walk on the plank in the right direction, so in a way, the mass moment is shifting in which direction? Towards the right. So man alone, let's say if the plank is not moving, if the only man is walking, so and man is going towards the right. So how the mass moment will shift? And the obvious answer is towards the right. Okay. But as per the center mass concept, we know that the center mass should not move at all. And that is only possible when the right shift in the mass moment should be compensated by the plank. It means the plank must move left by some value so that the product of shift into mass of the plank creates the exactly same mass moment shift as the man is trying to shift by moving right. And if these two shifts are equal, this will make sure that center mass has not moved at all. This is what exactly I'm trying to do.
Yes.
So the net shift in the mass moment of system must be zero because we are not allowing the central mass to move at all. And if one fellow will try to move it left, the other fellow has to move right or vice versa in order to balance the center of mass. Because shift in the mass moment is basically way of saying that the center mass may shift. But if we have more than two bodies or two or more than two bodies, then eventually the all shift will balance out each other and then center mass will remain there. So it looks like that things are in motion, but if you look at the center mass position, it is not moving, it is fixed, it's not changing at all. So this is what exactly we are trying to solve, the center mass concept, or this way of thinking. So because the system was at rest, it was not moving at all. And if the man suddenly starts walking, then this event is generated because of the internal force. So when a motion begins by virtue of some internal interaction, that will never affect the center mass. That's the idea. So center mass was at rest, so it will be at rest. Or even if it was in motion with some velocity which we don't know, then that will be constant. So that is the core idea behind solving this problem, that center mass should not move. And so, because center mass should not move, so the term I should use is the summation mi delta xi, the summation. If you write for each individual particle and if you add up vectorly, it must turns out to be zero. Else, a non-zero value will also make sure that there is delta RCM, which is also non-zero. So now the question is how we calculate it, how we do it. So the question was basically the question I haven't completed. The question was that find the find the okay, find the displacement of the blank when man reaches the another end. And the length of plank is given as L. So I want to know that in the process when the man will go towards the right, the plank must have moved left by some value which I don't know as of now. So I want to know what is that displacement, if that is a question. So before I give you the solution, which is pretty easy and obvious, can you try this question? So what you have to use is M, capital M and L. These are three parameters, I mean variables or some numbers which you have to use to express your answer. So maybe I should give you 2 minutes to solve this question. Start.
Sir,
Yeah.
sir, the plank has traveled in the left direction
Hmm.
by small l, small m into L by capital M.
Hmm. But that is not the right answer. So something has gone wrong. Can you identify what has gone wrong? So are you sure that the man has moved L distance in the ground frame? That's important. So when we write the displacement, we are writing the ground frame, and L is the displacement in the frame of plank itself, not in ground. That's very important. So your idea is correct. You have gone on the right path, but can you consider this part that L is not the displacement of man? The man has not gone right by L. It has gone right by some less value. Can you guess what value? What is the displacement of the man in the ground frame?
Sir, 0.
Man, not the system. Only man. So imagine yourself standing in a bus, and you're on the back seat of the bus, and from there you walk towards the front end, and meanwhile the bus goes backward. So in the ground frame, how much you have walked? That's the question. So to do this problem, it's very simple. So let's say the plank has gone left, because that is the plank is moving on the ground. So I can say let's the plank has moved by value x, which I don't know, but let's call it x. And man has walked in the frame of plank to the right end. So man is here. Okay. So
Sir, X relative.
so what is the displacement of man in the ground plane? Let's take right as first. So what is the displacement of man in the ground frame? That's my question. Towards the right. It is definitely L minus x. That's obvious. So you go L right, but the plank takes you x backward. So the net right movement is L minus x. Is this clear?
Yes,
Yes.
sir.
So this is the displacement of man. What is the displacement of plank? Delta x plank. It is towards left, so I can put minus x because we are taking displacement value, and I'm taking the right as positive, left as negative. So you could have also taken this as x minus L with negative sign. That's also okay because it's the same thing. So you can say that the man has gone left by x minus L because you have gone x behind, and you have also walked L right. So the net left displacement is x minus L. So it is up to you to interpret right or left. Okay. And then what the formula says that because the individual mass moment shift, not displacement, the mass moment shift in mass moment, which we say, should take place in such a way that m into delta x plank plus small m into delta x man, this must add up to 0 because that is how we can save the center mass shift at all. So we don't want the center mass should shift, and why it should not shift because we have discussed. Why? Because I don't want to discuss again. And now this will lead to the a very simplified answer. So m and delta x plank is minus x plus small m, and the delta x man is I'm writing L minus x. It's the same. And now I'm done. Kind of I'm done because this is 0. The moment you solve this, the x will be ml by you can see the answer having the sum of mass in uh, the denominator. L is called the relative displacement, not the absolute displacement in the ground plane. So you go from one end of the plank to the other end. Now the same plank problem they will be asking you in the like there is a man on a boat sitting on one end, then he walks and goes to the other end. So if a man will move from one end to other end, and if the boat is on a pond or a lake, the the boat will also displace. Now if the boat is really heavy, if m is really bigger, let's say if this m becomes too large, then you won't be able to see the shift at all. So generally, if we talk about the cruise, which is in millions of tons, so on a cruise, if a man will go from one end of the cruise to the other end, that will never shift the cruise at all because that x will be negligible. But if we have objects which are almost of same dimension, then the shift will be very much prominent. You can see the shift, and that happens when you try to jump from a boat. So the boat goes backward. In a way, you're pushing it back. So those things are visible in the even day-to-day life. It all depends on how heavy the boat is or the plank is. So let's do the next problem. So this is the floating restaurant somewhere near the gateway of India. And the whole idea of this water and the restaurant is that there is no friction force acting between the water. That's the idea. And the water is not moving up and down. So let's assume there is no wave form. So a family goes on a trip to this, I mean, to enjoy this restaurant because of its scenic location and, of course, adventurous placement. And now the man having two kids, and because their dad has taken away their mobile phones, so they are very sad. You can see they are sitting at the edge, feeling not good. This is a Bunty and Bubbly list on M1 and now, of course, the plank is having some mass. Let's call it Captain. But because he has gone for the vacation to enjoy the lunch, so that I mean, dad has ordered some maybe jalebi, and there's a table, of course. Table. So right now the man is enjoying near the table, and this is the jalebi. To make the location premium, let me draw some. So this is really a premium problem that we are going to solve. So what I'm going to consider is that this entire table, chair, man, and the umbrella. There are so many things. So this entire mass, let's call it small. So you can see there are four masses basically: small m, capital M, M1, M2. Now the next information that is given that the M1 is at a distance L1 away from the table, and M2 is at a distance L2 from the table. So we are ignoring the size of the man object and all our point object. The moment the order comes to the table, the dad calls Bunty, Mowgli, come and let's enjoy the jalebi. So although they were sad, but jalebi is something which the kids love. Let's say I don't know what nowadays whether you love or not, but in my time I used to love jalebi. So the moment this announcement was made, they ran up to the table. Okay. So now the question is, in the due process, when both the kids will reach the table, what will be the displacement of the plant or the restaurant? So question is, if M1, M2 goes to the table, then how much blank will displace? So that is the question. Okay. So it's pretty easy. Probably you can do in one line. So let's attempt this problem and then I'll solve for sure. So I'm giving you again 2 minutes to think and then maybe 1 minute to solve. So 3 minutes is okay, good enough. Okay. So
Yes,
start
sir.
doing this problem everywhere.
Sir, the small m is not moving.
Of course, S volume is fixed quantity, no? So the table will not move, isn't it?
Yes, sir.
I don't know why I want to move the table.
Sir,
Hmm.
sir, I got x is equal to
Hmm.
m2 L2
Hmm.
minus m1 L1
Hmm.
by m2 minus m1 minus capital M.
So in the denominator, all will be positive. We add all masses, so there is no question of negative sign. But fortunately or unfortunately, your numerator is correct. So you have to be careful what you add, what you subtract, because you need to understand the displacement in the ground frame. So when you write the displacement in the ground frame, you have to be very careful. Like should I write plus, minus, or whatever? So right now you have no idea whether the plank will move right or left. So there is no problem that if you assume right as your assumption, and if the answer turns out to be negative, it means you're going left. But eventually the answer will be correct. So what you can do is you can choose the direction of displacement of the plank either left or right. So let's begin with x towards the right. So the beginning of problem is always from the bottom. So we say that let's say the plank has gone right by x. This is the assumption we started. And the moment we make the first assumption, all other displacement becomes meaningful. So how much plank has moved? Mx. How much m2 has moved? X minus L2 because it's going left. How much m1 has moved? X also and L1 also. How much the table, chair, and his their papa m has moved? It is also x. Why? Because they are also not moving. But this all add up to 0, and you're done. This. So m plus m1 plus whole into x equals to m2 L2 minus m1 L1. That's the only answer. So still, I think some of you are not getting the point I'm trying to convey. So you begin with the assumption that the plank has gone either right or left by x. It really doesn't matter which direction you choose. Why it doesn't matter? Because if it is negative, it means the choice was made opposite to actual. And if it is positive answer, it means you correctly made the choice. So there is no problem with that choice actually. And then what we are supposed to write is mi delta xi for all objects, and then you equate to 0. Okay? Not okay.
Yes, sir.
Understood?
Yes.
So if I remove this page, can I do it again?
Yes, sir.
So don't do that. Let me give you another problem and you can practice on this problem. So if anyone having any doubt, you can just let me know, because this program only you have to solve. So I'll give you 2-3 problems and I will never give you the solution, whether I'll give you the answer. And you can figure it out why this is the answer. So this is the next problem. So this is a wedge. There is a wedge and the height of the wedge is small. That's given to us. And the wedge is of course movable because the mass of wedge is also given. There is a small block kept on the top of the wedge. The mass of the small block, let's call it m. And all surfaces are smooth. Yeah, you heard it right. All surfaces are smooth. So there is no friction between the block and the wedge. The question is find the displacement of wedge by the time block reaches the bottom. Now, the moment you release the system, the block will go down and right basically. I mean, if you remember the laws of motion chapter I have discussed, and the wedge will go towards the right. That's for sure. So can you tell me how the center mass is moving? Is it moving right, left, or at some angle? So in the due process, can you tell me what is the direction of center mass motion?
Yes, sir.
So 1, 2, 3, 4, 5. What is the correct path of center mass? What is the correct path of center mass motion (ACM) for the system of block and wedge?
So it is in second direction, like 2.
Second direction. Anybody else?
So 4.
Who said third?
So 4, 4.
Fourth. Who said fourth?
So nice.
Sir, I said 2.
Okay. So 2 and 4. Anybody else like want to guess some random answer?
Sir, it will be 3, 3, 3.
Now this is something really big. Now, when you try to basically answer the question based on motion perception, there is a very high chance that you may make mistake. So think in terms of force and ACM, and probably the first definition of ACM is more useful to you. So if you look at the entire system and if you think of external force, so what will be the external force to this system of block and wedge? Can you tell me the force acting on the system, not individually, system?
No,
Sir, the
Normal. Which normal? Normal between the block and wedge or normal from ground and wedge?
sir, the block and wedge.
Then again you made a big mistake. The block and wedge is a system, so that force is internal, so
It's
we
a
should not be
block and wedge
bothered.
system. Okay, sir. Then
sir, the gravitational
Yeah,
force
my
acting
question
moving
is
downward.
what are the external force for the system of block and wedge? So I'm
sir,
taking
the
block
ground and wedge. No,
and ground and wedge.
wedge
Okay.
normal.
Now that is the external force. Is there any other force acting as external?
Sir, mg downward.
Mg downward. Okay, that's correct. So is the net force acting down or net force acting up? Or net force is zero? So what do you think?
Zero.
So do you think that the normal is balancing the entire weight?
No.
If you think it is happening, then the small block should not move down,
Yes, sir.
which means if the small block is going down, which is simple indication that center mass is going somewhat down. So one thing is clear that center mass is going down for sure. I don't know about left and right, but I can very soon explain that there is no net force acting on the right side. So center mass cannot move from left to right. So from the ABD, which is N and mg for the system, which I will write something like this. Look at this very carefully. So these are very, very important ideas. So if I call this as N, and if I take mg here and mg here as external force, in this entire ABD, do you see any horizontal force? Yes or no? Anybody who can see the horizontal force?
No.
No. And because there is no horizontal force, so do you think that there will be some acceleration along horizontal direction?
No.
Definitely no. So one thing that we can say without confusion that ACM, the X component for the above situation must be zero. But ACM in the Y direction is non-zero. And in fact, we can determine the same. Okay.
Yes.
Okay. All right. So I think because this is zero, this implies either VCM X is zero or VCM X is constant. But because you release the system from rest, so this will be the correct answer
VCMX0.
because the system was released from rest. So this is the correct answer, and this will lead to the fact that delta XCM is zero, and this will lead to the fact that summation of mi delta xi equals to 0. Now this is again the end result of all these discussion. So is my question. Find the displacement of wedge by the time block reaches the bottom of the wedge. So you need not to worry about the accession of the wedge. See the beauty of center mass. It will not ask you the, so irrespective of the fact what goes internally, what are the force in action, what is their individual acceleration, there are some results that can be answered directly without going into the internal detail or internal mechanism of working. And that is the consequence or the boon of this chapter. So center mass is such a powerful chapter that it gives you relatively very complex answer at the end result without actually worrying about the internal details of mechanism. So this is all due to the theoretical power, the power of this chapter. So this chapter is very powerful theoretically. So it looks like a simple formula, but it is really hard to apply. So in general life, you cannot master this chapter at one go. So you need to first realize what is going on. So most of the case, a student will never master this chapter unless they can master some formula, but they do not realize what chapter is trying to convey. And the way I'm trying to teach this chapter is to convey the underlying message of this chapter. So hopefully you should understand this chapter in a better way. That is my goal. And I'm going to take this chapter to a different level because this chapter and the next chapter are the backbone of physics. So you should be good with these two chapters. Okay. So can you try now this question and tell me the answer?
Yes, sir.
Yeah.
Sir,
Yes.
so the displacement of wedge is
Mhm.
by the time it reaches the down is small m into h by tan theta into capital M.
Once again. How much you said? H by
Um,
tan theta into,
m m by capital M.
oh, not m by capital M. This one.
Yes, sir.
I think you made the same mistake which you made earlier. So when you take the displacement of one object, the other will also affect. So if you know the wedge has gone right by x, the block will go how much? And you are supposed to write the displacement of each particle or each moving object in the ground frame, not in the wedge frame. So your answer is because you have taken the displacement of the block as h by 10 theta, right?
Yes, sir.
And you know that is not the right answer. So the displacement of the block is basically x minus h by 10 theta towards the right. This is the delta x block, and delta x wedge is obvious, taken as x towards right. So when the block will reach bottom, the horizontal displacement of the block is how much? This much. That is quite obvious from the geometry. We can calculate this answer. This is how much. So this length is how much? We want a horizontal value. So this is h by 10 meter. You can attach h by. So when the block will reach bottom, by the time it is here, the wedge has gone right by x value. So what is the net displacement of the block towards right direction? So it is x minus h cot theta. This is what we write. So is this clear to all of you?
Yes.
So what the formula says? The mass of the wedge into delta x wedge, mass of the block into delta x block, and this must equals to 0. And so the answer is simple, mh.
Sir, but they both are moving different directions, so there will be.
Pardon?
So they both are moving in opposite directions, so there will
Mhm.
be minus sign. No?
Pardon? Okay, no, so I have taken the right movement. You can take a left, that's okay. So if you want to take the left value, so you write this as h cot theta minus x. Understood?
Yes, sir.
And then you write minus sign. So you write minus small m into h cot theta minus x. Correct?
Yes, sir.
So it will give you same answer. Correct?
Yes, sir.
Yes.
So I hope you have understood what happened in this entire discussion. So let's go to the next concept. I mean, in the same problem, can you also calculate, also find? I want to know that in the process, how much centromass shifted in the y direction. This is my question. What is the vertical shift? So what is the vertical shift? So instead of formula of writing delta x, you can write delta y for each object. And you will realize that the wedge is not going down. So there is no delta y wedge, which is 0. So you're supposed to add the delta y of block itself. So the simple answer is minus mh by m plus. Understood?
Yes, sir.
And there is something very interesting we can also see some very interesting results. But what is the total loss in potential of system? There are two ways you can write the loss due to each object separately, or you can write directly the total mass m g delta y. Yes. And if you solve, you get the answer is minus mgh, which you would have got by doing individual calculation also. So the potential energy is basically lost due to the delta yc. So if you have a system and if someone is asking you find the loss in potential energy or change in potential energy, so you can add the total mass into g into delta yc. Or if you know individual displacement in the vertical direction, you can just calculate individually and add up. So you will get the same answer. Okay. So what I have used the formula which I have used is summation mi delta yi for each object, and then you divide by the total mass. So there are a variety of things that we can do it from here. But is this the only thing you can do? The answer is no. You can do something more rigorous from this concept. Now, this is something we haven't taken care of. This is something big. So let's try to realize the consequence of this and the application as well. So in the laws of motion chapter, we have solved a variety of wedge and block problem, which you can go back and refer to maybe today after class. So I'm going to pick up some leaf from that chapter and will demonstrate the power of center mass. Some of the challenging problem of laws of motion can be solved fairly easy and almost in 1 to 2 lines with the help of course, this particular concept, center mass. So let me do again a wedge, because that is the question. This is the wedge of mass and okay, I'm just taking a block anyway. Not necessarily top, just and all surfaces are smooth. So there is no friction I'm taking. So because of the discussion that we just had, what we can say that center mass cannot accelerate horizontally. So ACX is 0. And for the obvious reason, because the net force acting the horizontal is 0. So I can relate the acceleration without doing any calculation, because what we know something. So what we know is that we know the formula m1 a1x m2 a2x, because we have just two, so I'm adding up to 2. You can add for 3 also, and because this is the formula, and this turns out to be 0. So this will again refer to something interesting. The numerator must be 0, then only it can be 0. There is no other way. M1 A1 x plus M2 A2 x, this must be 0. Now this is the guiding equation of this particular problem. Now again, this is very, very important. Okay. So we are trying to see the power of center mass. Center mass is a chapter which requires or demands a very deep understanding. It's not about formula, because even though you know the formula, probably you won't be able to apply in any numerical because that understanding is not there. So if you want to master this chapter, then you have to be good with the theory part. I mean, in fact, very good with the theory part. Okay. So now let me make some assumptions. So I know the wedge will accelerate, right? So I'm calling MA. I mean, A is the acceleration, I'm assuming. The block acceleration is quite complex, as we have seen before also. So block will slide down with respect to wedge. It's not ground motion. And at the same time, the block will also go right because of the wedge constraint. So the block is going to have two different axes, and I'm calling it AR, and I'm calling this is A. So what is AR? Acceleration of block with respect to wedge. And A is the acceleration of wedge for sure. So now this is the uh, assumption of course. So I hope you have understood the assumption which I have made about the block. The block will have two axes, A towards right. So let's say if the block is not moving down the plane, so it will move together with the wedge. So whatever is the acceleration of wedge, that will be given to the block for sure. And apart from that, it is having one extra acceleration going downward. And now we have figured out that the center mass cannot accelerate horizontally. So the acceleration will have some relationship. The horizontal component of acceleration will have some relationship that must be satisfied. So this comes at the angle theta. And so the horizontal component of this will be AR cos theta. And I'm not drawing the vertical component, although let's say this is. So now, what is the acceleration of the small block along, let's say, x is this, this is x. So what is the net acceleration of block along x dash? The value, the net acceleration along x. Can you tell me? Someone, please tell me the total acceleration or the net acceleration of block in the x direction. Anybody there?
A minus R cos theta.
A minus AR cos. Where?
Cos
And what about the wedge?
A.
A. And now we are done. So we know that it is M plus capital M into A is equals to small m AR cos theta. Okay. Equation 1. You can put it like this. Okay. And what we know about the block, that the net force acting down the plane is how much? What is the net force acting down the plane on the block? So for block, along the plane, the net force is gravity only. which is mg sin theta. Do you remember? So
Yes.
if you do the ABD, the force acting down the plane is only mg sin theta in the ground plane. And if this is the net force, then this must equals to mass into net acceleration in the ground frame, which is generally we don't write. So what is the net acceleration in the ground frame? Can you see that? Down the plane, what is the acceleration?
Yeah.
It is AR minus A cos theta. Again, this is something which you don't realize. So this A will have a opposing component and AR is down. So net will be AR minus A cos theta. So now we have a very simple answer that AR we can write as A cos theta plus G sin theta. And that is the purpose. So once I substitute AR here, I can get the acceleration A because that is what generally they will ask you to calculate, find the acceleration of wedge. And you can see that I have got the answer applying laws of motion for block only. And then the acceleration relation was obvious because of this center mass concept. So combining these two has reduced the effort exponentially. So I'm not writing the ABD of block and writing the all laws of motion, normal, gravity, and their component. But I'm using the a small piece of laws of motion with a small piece of center mass concept, and this is together giving me the answer. So that is how the center mass concept is will be at your rescue to solve some of these challenging problems. That is always the case, and most of the challenging problem of centrum and laws of motion are based on this particular concept which I just discussed. So for your examination, going any deeper is not required. If even if you know up to this level, it's more than sufficient to get a very good rank. I'm not saying the topper of Olympiad, but J you can qualify or any examination you can qualify. This is sufficient knowledge. So I will not go deeper than this. This is sufficient for us, and I'll go to the next concept. So maybe I can end this topic with this very problem, which I want you guys to solve. Mm, this is the problem. So there is a rod which is fixed at both the ends rod is smooth and there's a bangle. Bangle is something which you put. So the bangle can slide. Bangle can slide on this rod freely. And it is having some mass, let's call it capital. And now from this bangle, we have a thread attached to a object of mass that's small. Now the moment you release the small mass m, which is connected with the thread, it will swing down. But the moment it will swing down, something interesting will happen. So the moment it will tilt, the tension developed will have horizontal component which will accelerate the bangle or the we call it collar towards the right. Gravity will bring the small mass down. The big mass cannot move. And if you think of the system, calling M and M as a system, if I say capital M, small m is my system, then again the same problem will arise. There is no horizontal force acting on the system, and therefore the center mass cannot displace horizontally. So your question is, find the displacement of bangle by the time the string becomes vertical. And I'll give you exactly 2 minutes to solve. I'm waiting. Okay, done. I think I have given sufficient time. So what is the answer? Put some effort to get the answer. If I only give you answer and if you only look at the answer, that will not make you any better. So of course, by the time the string is becoming vertical, the bangle will displace by somewhere. So just call it x. So what is the displacement? Now, if this is the x, this will be how much? If you look carefully, that the this hanging mass is moving left by L minus x, and the bangle is going right. So the answer is simple: mx minus m. And it's the same answer again and again. If you look at the pattern, we have been getting the same answer. So with this question, really we can stop this particular topic and we can move to the next concept or next topic. Okay, so the next concept or next topic is going to be impulse and momentum. Okay, so this is what I will discuss in the next lecture. So I think Wednesday. All right. So see you in next lecture, and you can practice from the sheet which I have shared, and you will be able to solve a variety of problems. Just wait. Let me tell you which question you can solve. Mm, um, I think I have shared the sheet with all of you guys, right? St. Thomas I have shared, isn't it? Okay, let me share it again. Am I audible, guys?
Yes.
So you all have the sheet, right? That sheet I shared long time ago.
Hmm. Okay. So now you can solve the exercise 1, section B complete. Exercise 1, part 1. Exercise 1, part 1. This is the, yeah. Then you can go to the next is mm, again in part 2 also. So part 2, again the same section.
Uh, then exercise 1 part 2 matrix match 2, sorry, part 3, this is part 3, match the column 2. This is what you can solve now. Then from exercise 2 part 1 you can solve the part 1. Yeah, so it's a mixed match question, so just check the question which you can solve, just solve it. That's it. And, all right, this is your homework.
Hello, sir.
Yes.
So please will you repeat because I was not able to hear it is cracking.
So I have written everything on the board. You can read from here. So this is your homework from the sheet. And the sheet I have again shared those for those who have not received earlier. You can download now and start solving. So from exercise 1 and exercise 2, exercise 1, part 1, part 2, and part 3, match the column 2. So this is, or this will be your homework. We'll see you next class. Bye and take care.
Bye, sir.